Imagine for a second that you are an auditor for a self-driving car company.
Right. A pretty high-stress job.
Well, absolutely. So a vehicle just made a split-second decision based on a highly complex, multi-layered algorithm. And naturally, you sit down with the software engineering team and ask them to explain exactly why the system was designed to make that specific choice.
You'd want to see the receipts, basically.
Exactly. But in response, the lead engineer just kind of shrugs and tells you, well, the AI optimized it. I mean, I can tell you right now that is absolutely not going to fly with regulators.
It definitely won't. I mean, when you're dealing with safety-critical systems, things like autonomous driving, aviation software, or automated medical devices, a shrug is essentially a massive legal liability.
Yeah, you can't just guess when lives are on the line.
Yeah, precisely. You need an airtight, mathematically sound justification for every single line of code and, well, every single system requirement. The stakes are simply too high for black box guesswork. If a system fails, investigators really don't want to hear that a machine learning model just sort of felt like it was the right move.
And that exact scenario is really the driving force behind this deep dive. Today, we are exploring a really fascinating research paper published in IE Access.
It's a great paper.
Yeah, it's written by Hao-Wei Cheng and a team of researchers from Waseda University and ASM Corporation. And we are looking at this completely new framework called ArgRE, which stands for Argumentation for Requirements Engineering.
Right, ArgRE.
And our mission today is to unpack how this framework forces AI agents to literally debate each other using formal logic. Like, we're going to look at how we can stop AI from making these opaque compromises and instead force it to generate a perfect auditable trail that explains the rationale behind every piece of software it helps design.
And this is incredibly timely, honestly. We are looking at a way to fundamentally fix how artificial intelligence handles conflicting goals. But, to understand why a specialized logic framework is suddenly necessary, we first have to look at how software is currently built.
Right, the baseline.
Exactly. We have to see why the standard process is already struggling under its own weight.
Yeah, because before we can point fingers at AI design, we kind of have to acknowledge that human-led software design already has some massive vulnerabilities.
Oh, for sure.
The paper highlights this staggering statistic. Empirical studies show that over 70% of failed software projects fail entirely due to requirements-related issues.
Which is huge.
It really is. We aren't talking about bad coding or typos in the syntax. We are talking about incomplete goals, ambiguous wording, or just unresolved conflicts between what different stakeholders actually want the software to do.
Right, and that 70% failure rate happens when human engineers are at the wheel, trying to balance dozens of competing interests. So, to speed up this incredibly dense process, the software industry has started relying heavily on multi-agent large language models, or LLMs.
Right, the multi-agent approach.
Yeah. You essentially assign different AI agents to represent the different goals of a system. You have one agent acting as the advocate for safety, another fighting for operational efficiency, and they're supposed to collaborate to write the foundational rules of the system.
Which, I mean, on the surface, that sounds like a great delegation of labor, right? Let the AI handle the brainstorming. But the paper points out a massive flaw in how these multi-agent systems currently resolve their disagreements.
The heuristic synthesis problem.
Exactly. They rely on something called heuristic synthesis. Basically, when two AI agents disagree, they merge their conflicting requirements implicitly. They use these opaque, weighted mathematical averages to output a compromise, but they leave absolutely no trail explaining the logic behind that compromise.
No trail at all.
Yeah. Okay, let's unpack this with an analogy. It's like a group of roommates trying to set the apartment thermostat. One wants 65 degrees, the other wants 75. They argue, get exhausted, and just set it at 70.
A classic compromise.
Right. But when the massive power bill arrives at the end of the month, no one remembers why they chose 70 or who actually needed the air conditioning running in the first place.
That thermostat dynamic is actually the perfect way to visualize the problem. And in regulated software engineering, that forgotten reasoning is what the researchers call the formalization gap.
The formalization gap, right?
Yes. It is the total absence of a mathematically grounded framework to justify why certain requirements were accepted while others were rejected. In your example, setting it to 70 degrees is a heuristic compromise. It's a guess that just sits in the middle.
Which is fine for a living room.
Exactly, that works for a living room. But under strict regulatory frameworks like, say, the EU AI Act's Article 11 or the Automotive Safety Standard ISO 26262, you cannot just split the difference. You must provide an auditable trace of your engineering choices.
Because if a self-driving car gets into an accident, You can't hand a regulatory investigator a report that says, well, the safety agent wanted a highly conservative speed limit, and the efficiency agent wanted to optimize the commute time. So the system just averaged their numbers out and hoped for the best.
Precisely. Splitting the difference is mathematically indefensible in a regulated environment. You need a system that doesn't just average numbers, but actually argues its case. And this is where the researchers introduce ArgRE.
Okay, so how does it work?
Well, the core innovation of ArgRE is that it embeds a concept called Dung-style abstract argumentation directly into the AI's negotiation phase.
Dung-style abstract argumentation. That sounds incredibly cutting edge. But the paper notes this is actually a logic framework from 1995, right? Created by a computer scientist named P.M. Dung.
Yeah, it's been around for a while.
It's wild that a theoretical logic model from the 90s is turning out to be the key to managing modern generative AI. So how exactly do these agents use this framework to resolve their conflicts without just defaulting to an average?
To make it work, the framework deploys 5 highly specialized AI agents, and it guarantees that they will disagree.
They are built to fight.
Basically, yeah. You have the safety agent, whose only job is reliability, the efficiency agent, pushing for speed and low resource consumption. Then you have the green agent, advocating for environmental sustainability and energy footprint.
Okay, so safety, efficiency, green. What are the other two?
The trustworthiness agent, which handles security and data privacy, and the responsibility agent, tasked with ensuring ethical alignment and legal compliance.
Wow, so a lot of cooks in the kitchen.
Exactly. When you give them a software project, they immediately start clashing. Dung's framework models this negotiation by forcing them to use 3 deterministic attack patterns. It maps every proposal, critique, and refinement as a node on a mathematical graph.
Wait, let's actually unpack that mechanism for a second because I want to visualize how these attacks work.
Of course. Picture a massive whiteboard. Every time an agent speaks, a new node is drawn on the board. The framework restricts their interactions to 3 specific moves.
Okay, what's pattern 1?
Pattern 1 is a direct critique. Agent A proposes a requirement, that's a node. Agent B issues a critique saying, hey, that violates my constraints. A line is drawn from the critique to the proposal. That is an attack.
Got it. Direct attack.
And
pattern 2.
Pattern 2 is when a refinement supersedes a proposal. So Agent A realizes their first idea was flawed, so they submit a better version. That new version mathematically attacks and overrides the original proposal.
Okay, that makes sense. It's like self-correction.
Exactly. And finally, pattern 3 is the counterattack. A new refinement attacks an opponent's critique, effectively neutralizing the objection.
But wait, if we are explicitly programming AI agents to actively attack each other's parameters, doesn't that just lead to an endless, unresolvable robot screaming match? I can easily imagine 2 AI models just firing pattern 1 critiques back and forth until the server crashes.
That is the exact risk with autonomous agents, but what's fascinating here is how the ArgRE framework prevents it. It enforces bounded dialectical rounds. Think of it as a highly structured, timed debate. Thesis, antithesis, synthesis.
Okay, so there's a time limit.
Yes, the system limits the absolute number of rounds they can engage in. But more importantly, it monitors the mathematical similarity of their text outputs during the debate to see if they are converging on a solution.
Ah, to see if they're just repeating themselves.
Right. If they start repeating themselves, the round is terminated. So what you are left with isn't a screaming match, it's a directed graph of logic. It forms a literal web of nodes and edges that proves a requirement was rigorously tested from every conceivable angle.
If you're listening to this and wondering how all these nodes and attack patterns actually translate to the code in your life, the paper provides a brilliant real-world case study.
Yes, the autonomous vehicle example.
Right. They applied this to the perception subsystem for a level 4 autonomous vehicle. So picture the fully self-driving car you might take to work. It has radar, it has cameras, and it has to fuse all that sensor data together to build a 3D map of the road around it.
And the moment that project starts, we get a severe conflict. The safety agent analyzes the requirement and proposes a 500 millisecond time limit for sensor fusion verification.
Which sounds fast to a human, I guess.
Right, but it wants a highly conservative dual-channel check to absolutely guarantee the data is accurate before the car makes a move.
Now, if you are wondering why a 500 millisecond delay matters, think about the braking distance of the car you drove today at highway speeds. Half a second is a massive distance, which is why the efficiency agent immediately steps in and issues a pattern 1 critique.
Efficiency is not happy.
Not at all. Efficiency says absolutely not. We have a 30 millisecond real-time planning cycle budget. If we take 500 milliseconds just to look at the sensors, the car has already traveled too far. The data is stale.
In the old heuristic model, the AI would just average 530, spit out 265 milliseconds, and blindly move on, which frankly fails both the safety guarantee and the real-time planning constraint.
It's the thermostat problem again.
Exactly, but under ArgRE, that pattern 1 attack forces the safety agent back to the drawing board. It has to refine its proposal. So safety comes back with patterns 2 and 3. It proposes a two-stage pipeline.
A two-stage pipeline.
Okay. It creates a fast path that takes less than 30 milliseconds to handle 95% of normal, everyday driving scenarios. But it reserves a thorough path of 500 milliseconds strictly for complex anomalies.
Here's where it gets really interesting. Because it's like trying to do a meticulous 100-point inspection of a car, but you have to do it while driving through a fast food drive-thru. Safety wants to be thorough. Efficiency wants to keep the line moving.
That's a great way to put it.
But okay, mathematically that works, but does adding a two-stage pipeline introduce completely new risks regarding system complexity? Like, does splitting the process actually end the debate?
Not immediately, which is really the beauty of the system. The efficiency agent reviews the two-stage pipeline and critiques it again.
It's persistent.
Very. It argues that the thorough path might block the system's processing threads. Efficiency demands that the thorough path must run asynchronously in the background, and it pushes the fast path requirement from a 95% success rate to 99%.
Wow, so it's raising the bar.
Right. And this forces the safety agent to refine one last time, proposing a final 3-component architecture that balances the asynchronous thorough path with the hyperfast primary path. At that point, the efficiency agent's constraints are met, the attacks stop, and consensus is reached.
So this generated trace card is essentially like looking at the structural blueprints of a bridge. Every single argument is a load-bearing beam.
Yes, exactly.
If that auditor from our intro comes back and says, hey, why is your safety check running asynchronously in the background? That seems like a strange architectural choice. The engineers don't have to shrug. They pull up the graph.
You have the proof.
Right? They could point to the exact node where the efficiency agent attacked the original proposal and the exact node where the safety agent reinforced it with the asynchronous refinement. They could prove the structure is sound.
Exactly. It proves that the 500 millisecond rule wasn't just casually relaxed. It was systematically re-engineered to meet a physical constraint without sacrificing the safety guarantee. But, having that massive map of arguments is only half the battle.
Oh, what's the other half?
You still need a mechanism to look at that web of attacks and defenses and mathematically declare a winner. You need a judge to prune the graph and decide which arguments ultimately make it into the final software specification. This introduces the concepts of grounded semantics and preferred semantics.
Right. Let's start with grounded semantics, because the paper describes this as the highly skeptical, ruthlessly conservative approach. How does the system use this to prune the graph?
Under grounded semantics, the algorithm scans the entire graph of nodes. A software requirement only survives if it is entirely unattacked from the very beginning, or if every single attack against it has been perfectly neutralized by another accepted argument.
So it has to be flawless.
Flawless.
Yeah.
If there is a single node with an undefended attack pointing at it, the system prunes it. It throws the requirement out entirely. It is a zero-trust model.
Wow. Zero trust.
Yeah, and this is the ideal setting for domains like autonomous driving or robotic surgery, where you only build what you can absolutely prove is safe.
That makes total sense for life or death software.
Huh.
But I imagine there are software projects where you want a slightly more flexible approach.
Yeah.
Which I guess brings us to preferred semantics.
Correct. Preferred semantics looks for the maximum defensible set of arguments, rather than demanding absolute perfection. And this is where human engineers are allowed to intervene by applying priority weights to the agents.
Oh, interesting.
Let's say an engineering team wants to prioritize sustainability. They can program the system to weigh the green agent's arguments slightly higher than the efficiency agent's arguments. This becomes crucial when the system calculates something called the Graph Cyclicity Index, or GCI.
Okay, let's unpack the GCI, because the paper leans heavily on this metric. What exactly is a cyclicity index measuring?
The GCI measures how often arguments get stuck in a mutual loop. Imagine the whiteboard again. The efficiency agent attacks a proposal by the green agent. But the green agent fires back and attacks the efficiency agent's critique with equal mathematical validity.
So they're just pointing at each other.
Exactly. You have an arrow pointing from A to B and an arrow pointing from B to A. It is a complete cyclic deadlock. Under the strict grounded semantics, the system sees that unresolved loop and just drops both nodes.
Just deletes them both.
Right. Neither requirement gets approved. But Under preferred semantics, the system looks at the GCI, identifies the loop, and then uses those human-assigned priority weights to break the tie. The heavier weight wins the loop.
Wait, if preferred semantics just lets human engineers weigh the scales so their favorite agent always wins the tiebreaker, isn't that just heuristic synthesis with extra steps?
Yeah.
Are we just hiding human bias behind complex graph math?
It definitely sounds like it at first glance, but if we connect this to the bigger picture, it is entirely different. The priority weights only apply to resolve those specific cyclic deadlocks. They do not give an agent the power to override the entire logic tree.
Oh, I see.
Yeah, an engineer cannot just crank the safety weight to maximum and force the AI to ignore a valid, undefended physical constraint raised by the efficiency agent. The attacks still have to be resolved logically.
That makes sense.
What the weights do is give human designers a formal, mathematically provable lever to control how conservative or liberal the AI should be when facing a perfect standoff. The bias is explicit, documented on the trace card, and only used when logic alone cannot find a winner.
That is a crucial distinction. It's not a blank check to ignore constraints. It's a highly documented tiebreaker for mathematical standoffs. All right, so we've explored the graph theory and we've walked through the self-driving car case study. Let's look at the hard data.
Yes, the empirical results.
Because the researchers didn't just theorize this. They ran ArgRE through 5 different software engineering case studies, comparing it side by side with the standard heuristic synthesis baseline. How did independent evaluators score the results?
The data is incredibly compelling, especially when you look at the decision justification score, or DJS. The researchers brought in independent human evaluators, software engineers, who were totally blinded to which AI system produced which output.
A true blind test?
Exactly. They were asked to read the final software requirements and score them purely on how well the reasoning was justified. ArgRE scored a 4.32 out of 5. The heuristic synthesis baseline scored a miserable 3.07.
Wow, a jump from 3.07 to 4.32 is massive. And that clarity directly correlates to another metric they tracked, right? Trace completeness?
Yes, trace completeness.
The paper shows that ArgRE averaged 40.9% on trace completeness. That means nearly half of all the accepted software requirements had a perfect, unbroken mathematical lineage tracing all the way back to the original proposal. You can follow the exact evolution of the idea.
And critically, it achieved that traceability without mangling the actual goals of the software. The researchers used a metric called BERT score to test semantic preservation.
What does BERT score do exactly?
BERT score uses neural networks to analyze the underlying meaning of text. It compared the initial requirements prompted by the human engineers against the final, heavily debated requirements output by the AI. ArgRE scored 94.9% on semantic preservation, perfectly matching the old heuristic methods. The AI didn't lose the core intent of the software while building this massive logic graph.
Okay, but looking at the final metric in the paper, there is one data point that seems entirely contradictory. When they measured compliance coverage, which tracks how many of the regulatory checklist items the final software successfully met, the old heuristic method scored 98.2%. ArgRE scored 84.7%.
Right, a significant drop.
So what does this all mean? Why would a vastly superior logic framework perform objectively worse on regulatory compliance? How is that a victory?
It is the most counterintuitive finding in the study, but it is actually the strongest proof that the system is functioning exactly as intended. The compliance score is lower because ArgRE, particularly undergrounded semantics, is merciless.
Merciless how?
It ruthlessly prunes any requirement that doesn't have a perfectly defended logic chain. The old heuristic method scores a 98% because it just blindly accepts flimsy, averaged-out compromises simply to check a box on a compliance form. It values the appearance of completeness over actual safety.
Ah, I see.
In safety-critical engineering, it is infinitely better to explicitly drop an unproven requirement and flag it for a human engineer to manually review than to accept a bad compromise just to score a 100% on paper.
Oh, that makes total sense. So the heuristic AI is basically a student faking its way through a multiple choice test by always guessing the middle answer just to ensure the whole page is filled out. Meanwhile, ArgRE is leaving the ambiguous answers blank, raising its hand, and telling the teacher that the question itself is structurally flawed.
That is the perfect analogy.
I would absolutely rather have the vehicle that raises its hand than the one that blindly guesses.
Exactly. ArgRE intentionally sacrifices a false sense of total coverage in exchange for absolute certainty about the requirements it does cover. It provides the literal receipts for AI decision-making.
As our world becomes increasingly reliant on AI to build the infrastructure of our lives, From the braking systems in our cars to automated medical diagnostics and financial security networks, the why behind the code becomes just as critical as the what. We cannot afford to let AI build our infrastructure in a black box. Frameworks like ArgRE give us the flashlight to see exactly how the sausage is being made.
It forces accountability back into the automation process. And frankly, the concept of forcing agents to graphically prove their reasoning goes far beyond just software engineering.
Which is a fascinating thought to leave you with. If we can successfully program autonomous AI agents to use a 1995 abstract logic framework to resolve their complex conflicts with perfect mathematically traceable logic, well, what would happen if we forced our own human institutions to use this exact same framework?
Oh, that would be something.
Right. Imagine mapping out the next highly charged corporate board meeting or a legislative debate into explicit attacks and refinements on a giant whiteboard. Every vague heuristic compromise would be immediately pruned. Every final decision would require an unbroken trace card of logic. The results might just be terrifyingly efficient,
I suspect a lot of hour-long meetings would suddenly become very short.
or at least mathematically rigorous. I
Mm.
would certainly pay to see the graph of that board meeting. Well, thank you for joining us on this deep dive. Our goal is always to give you the ultimate shortcut to being perfectly well-informed, and today we've armed you with the mechanics of how the future of AI software is being fundamentally re-engineered for safety. So the next time you ask an engineer why a system did what it did, and they try to shrug and tell you the AI optimized it, you just look them in the eye and demand to see the trace card. Catch you on the next deep dive.